Hi, my name is Brian Caffo, and this is a hodgepodge lecture, the final lecture from the regression models class in the data science series. I teach this class with my co-instructors Jeff Leake and Roger Pang, and we're at the Johns Hopkins Bloomberg School of Public Health in the Department of Biostatistics. Okay. So I wanted to show how you can fit functions using linear models. So instead of a linear model, a model that's a line or a plane, we want f of x, y equal f of x plus error, maybe an I right there. How can we fit such a model using linear models? This is called scatterplot smoothing. And so here I'm going to show you how to create a kind of stick breaking type model. Might look something like that, right? If your data looked like that, right? Where you knew where the breaks were. It's called splines, and so imagine if we know these knot points. I think that Greek letter is called Xi, and notice the little plus right there. I'll describe what that is in a minute. But imagine we have a line, and then we have plus these guys times some other parameters, and then our epsilon I. These guys are known. These are numbers. Given that we know our x's, we know these guys. Okay. Okay. So what this little parentheses plus means is it's a if a is greater than 0 and 0 otherwise. So -1 plus is 0, 1 plus is 1. 2 plus is 2, -2 plus is 0, and so on, right? Okay. And then you can prove to yourself that this function is continuous at the knot points. And what do I mean by that is let's assume a knot point is, to prove it to yourself, just do beta naught plus beta 1 xi plus xi minus 5 times gamma k plus, okay? And, figure out what this line is as x sort of goes to it from below 5, and then figure out where it's at as x goes to it from above 5, and you'll see that it hits at the same point. But that you have that below 5, right? Below 5, the line is beta naught plus beta 1 xi, right? Because below 5, these are always negative, and so the plus will turn them all into 0, so the whole term drops out. And then above 5, it's going to be beta naught plus beta 1 xi, right? It's going to be beta naught plus beta 1 xi plus xi minus 5 times gamma k, right? And this is going to be equal to beta naught plus 5 gamma k plus beta 1 plus gamma k, don't know why I'm keeping the k, times xi. So it's just another line, but with a new intercept and a new slope. And then if you have a sum of these things, it's just a new intercept and a new slope every time it approaches a new knot point. Okay, let's do it. It's really fun, depending on how you define fun. Okay, so I'm going to simulate some data. N is 500. X is just a sequence, and you'll see why in a second, why I picked 4 pi as the 0 to 4 pi is the limit of the sequence. And my y is sine x plus normal errors, okay? Then I'm going to just get a bunch of knot points. I'm going to get 20 knot points equally spaced somewhere along the way, and I don't know why I put knot points out past the range of the data. I think that was an accident. So my spline terms are, I'm just going to do this a plus function, this little spline function at each of these for each of my x values. And so my x matrix is going to have my it's going to have 1, it's going to have x, and then it's going to have all my spline terms that I just created. Okay? And my y hat is just going to be, if I predict my fitted linear model with y as an outcome, and this is my x matrix, and I'm subtracting at the intercept because I put an intercept in my matrix. Okay? And now I'm just going to plot my x and y. Okay, and then these are the points, and then I'm going to show the fitted model. Okay, and what you see, pretty neat, right, is that it fits these little sticks, right? You can see the little breaks in the lines, and it fits the data pretty well. It fits a pretty complicated function. What you might be saying is, probably what you're saying, probably not, but maybe, is that I really don't like these little sharp points. I'm really a rounded, well-rounded guy or gal, and I don't want sharp points. Okay, that's probably what you're thinking. So let's get rid of those. So if you add some squared terms, then it turns out that not only is the function continuous at the knot points, you get a derivative at the knot points. And if you added cubic terms, you get 2 derivatives at the knot points. If you add fourth order terms, you get 3 derivatives at the knot points, and so on. And what the derivatives mean is it looks curvy, not sharp and jagged, right? Okay. So here now we just have beta naught plus beta 1 xi plus beta 2 xi squared, and then instead of doing that, instead of doing just the plus function, we raise it to the power 2, where here a plus 2 means a squared if a is greater than 0, and 0 otherwise. Okay? Let's do that now and see what happens. Looks much better. Right? So now our spline terms are created this way. Only difference is I put a square right there, and then I have my model terms, my intercept, my x squared, and my spline terms. I'm going to get my fitted y's, and then I'm going to plot them, right? Plot the data points in the line, and then it looks like it's capturing it quite well, right? So that's how you can fit kind of complicated functions in R. Pretty neat. Only took 1 second to describe, well, a couple minutes. Let's go through some notes. This collection of spline regressors is called a basis, and to say that people have spent a lot of time thinking about bases for this kind of problem is an understatement. It underlies a huge chunk of statistics. You know, it's a big part of nonparametric regression. If you just want one knot point, then you can fit kind of like hockey stick type problems, right? And that, that's sometimes useful if you have data that looks like a hockey stick. And you need to kind of know where that knot point is. It's hard to estimate the knot point, so we don't cover that. Any rate, so that's good. You can now fit kind of hockey stick looking things. So it's also true that you can just do these things in GLMs, right? You just add the the little hockey stick terms in the linear predictor, so you can fit nonlinear functions is kind of predictors in GLMs. And I should have added, you can, if you want a kind of nonlinear confounder adjustment, you can add them, plus other terms in the model. So an issue with these, the main issue with these approaches is the large number of parameters introduced. And just to show you, right, when we did it here, the knots, however many knots we added, I think I added 10 knots because I accidentally put an 8 there. We added 10 parameters, right? If you look at the model, right, there's an extra parameter, gamma k, for every knot. So you're adding lots of parameters. And this idea of so-called regularization is really important in kind of modern statistics. And that's how you can get around that problem in a neat way. But we can't cover that just because it's kind of complicated. But recognize you just can't throw as many knots as you'd like into a problem without consequences. I wanted to illustrate that the so-called discrete Fourier transform is in fact actually just an instance of a linear regression model. And this goes back to this idea of bases, right? So the bases that we just discussed, these little hockey stick bases, right? So we had the intercept, x squared, right? You know, x looks like that, x squared looks like that, and then these spline terms kind of look like little terms like that. Okay, so that's a basis, right? You know, we have this. They're not orthogonal. Kind of the better bases are orthogonal, but people have orthogonalized those bases and they just give it another name, like. But there's some really famous orthogonal bases for fitting functions, and one is to have, you know, kind of sine and cosine terms of different periods, and the most you know, the sines and the cosines is the most famous version of that, and if you add enough of them in the right way, then you're doing exactly what's called the discrete Fourier transform. I'm going to give you kind of a taste of it. Not exactly the right thing, but just as an example, the four notes on a piano. So the notes at the scale of 4 are as follows for the following frequencies: 261.63. So that's C4, and then 523.25 is C5. So this is C, D, E, F, G, A, B, C. So let's see. So, and then I'm going to create a kind of time sequence. So imagine if you recorded 3 notes being played at the same time, which is the so-called chord, right? And you recorded them for, I don't know, I'm saying here 2 seconds. And so n is the length of t, okay? And so so these guys are the frequencies. Let me create a sine function at the C4 frequency, a sine function at the E4 frequency, and a sine function at the G4 frequency. So if you know, so this looks like it looks really fast. If you were to translate that into something that could play that function, it would sound like kind of a MIDI audio. Like, it would sound like doo at exactly the right frequency for C4. So if you've ever had an electronic tuner that plays kind of a perfect note, it's just playing these digital frequencies. So here's C, E, and G, and then my chord, it's just adding the 3 of those together. So there's my chord. So this would sound like a chord. Now, it wouldn't sound good. It wouldn't sound like a chord played on a piano or a guitar or something like that, because it sounds like you know, kind of perfect representations of those without all the interesting bits that a real instrument adds. And then I'm going to add random noise, which just sounds like crackling if you were to play it as an audio file. Okay. Now, so what I want to do, here's the task. I want to you know, given that I know that all I'm going to play is the kind of keys on a keyboard from C4 to C5, and I'm going to play them for 2 seconds, and I'm going to play them for the whole time for the 2 seconds, and I'm going to give you the data. I want you to write a function that then guesses what chord it is. Okay? So here I'm going to apply to those notes, I'm going to create my basis functions, which is just a bunch of sine terms, right? It's going to look, each one of these guys is going to look like that at a different frequency, where the frequency corresponds to the notes. Okay, so I'm going to fit the observe chord the chord that I observe as a function of my basis. I'm going to get rid of the intercept because I kind of know there's no intercept in the way that I'm doing this, but you could add the intercept if you want. And in this case, of course, I didn't actually play the chords, but you know, honestly, if you played them on a keyboard with the right keyboard setting, this wouldn't be that different. The only problem being you got to figure out, you know, how to digitize, how to get the digitized sound actually into R, which isn't that hard, but probably not worthwhile for this class. So here's my plot where I label the various notes, right? And I plot the squared coefficient, and you can see that it guesses right, that this was C4, E4, and G4, and that D4, F4, A4, B4, and C5 were not played in the chord. Okay? And so this is kind of a really kind of lame instance of the discrete Fourier transform. And all the discrete Fourier transform is doing exactly this. It's fitting a bunch of regressors that are a bunch of these trigonometric time series at this particular frequencies, so that they're and gets the coefficients. It does it in a the so-called fast Fourier transform does this in about the fastest possible way that you can. So actually doing this process of using LM to fit a bunch of trigonometric terms, if really what you want to do is the Fourier transform, it's an extremely slow way to do it relative to the fast Fourier transform. And here I show what happens if you actually do FFT, which there is an FFT function in R. So my A is my FFT of the chord, and I'm plotting the real component of the Fourier transform squared, and this corresponds to those coefficients. And this flipping over is this flipping over is just simply due to kind of periodicities and symmetries. When you look, you can see that if these are the frequencies for those three notes, but the Fourier transform is checking for a lot more notes than just the range of single octave that I put in my linear model function. So that's why the bars are a lot spikier. It's checking for all possible notes at all of the frequencies that it could detect, right? You couldn't detect frequencies faster than you sampled, as an example. So the Fourier transform is trying for all of them. Anyway, I thought you might find that kind of neat, that these kind of seemingly complex techniques like Fourier transforms can be related very cleanly back to linear models, and now you can actually go play your keyboard and have your computer guess what chord you're playing.